Hello everyone. In the previous lecture, we had a look into different methods of interpretation of vertical electrical sounding data. What are all the different methods? These are all the different methods of interpretation of the vertical electrical resistivity data, which we have seen in the previous lectures. One is asymptotes, then curve plotting method to determine the reflection coefficient, then inverse slope method, then S-line method. After that we had seen curve matching, then we had a look into partial curve matching. Towards the end we had seen the use of commercially available software to interpret the resistivity data obtained by vertical electrical sounding. In general, the data which we obtain can be classified generally into 4 different types, right. Suppose if you consider a 3-layer case, a classical 3-layer case, these are all the possible combinations which we may end up in getting during our field investigation. Accordingly, as a convention, these curves are named after some letters as K type, H type, A type and Q type. So, if the resistivity varied something like this, then it is called as K type, right, which is also pictorially shown here, right. Suppose if the resistivity of the layer increase and then decrease like this, right. Suppose if you end up in having a relationship something like this, that means resistivity of layer 2, this is layer 2, resistivity of layer 2 is higher than 1 as well as higher than 3, then you will have a curve something like this. This type of curve is known as K type. If you have a curve just reverse of K type, which is known as H type curve. In H type curve, the relation is completely different. Layer 1 is having higher resistivity, this is layer 2 is having lower resistivity, layer 3 again has higher resistivity. So, such a curve is known as H type curve. Then 2 other curves, one is known as A type. In A type, continuously the resistivity values of layers are increasing, then it is known as A type curve. Just reverse of this is known as Q type curve, where the resistivity of the layers are continuously decreasing. So, conventionally we are expecting any one of this curve. Suppose if you are dealing with a 3-layer case, I will repeat, if you do a survey in a 3-layer case, either we may get something similar to K type or something similar to H type or A, otherwise Q type curve, depending upon the type of formation that exists below the surface of the earth. Generally, we expect one type, something similar to A type or Q type or H or K type, right. And when we conduct the survey by 3D method, right, we are overcoming the issues which we have seen under the vertical electrical sounding. So, what are all the issues in vertical electrical sounding? It is difficult to deal with many number of layers, right, because conventionally only for 3-layer case we are able to quantify the thicknesses of layers. If layers are beyond 3, we can resort to partial curve matching, but in partial curve matching, if we make one error in the estimate of thickness of one layer, that is carried forward for estimating the locations of other discontinuities. Further, since we are dealing with 3-layer case, we always restrict ourselves only with these 4 types of curves. That is what we have seen just now. Suppose if you have multiple layers or there is large amount of heterogeneity, from location to location, it is difficult to compare one vertical electrical sounding data which we have obtained at station 1 with station 2, because lot of differences, right. That means, why do we have so much of difference? Layers may not be continuous as we assume in a 3-layer case. You may have different zones of, maybe this is clay, then you may have a sandy zone here, then we may have one more clay lens here. So, this complicates our interpretation. In such regions, we go for 3D or 2D resistivity tomogram. So, what is 2D or 3D resistivity method? Hope you can recollect, initially we had a look into electrical profiling method. What did we do in electrical profiling? This was the ground surface. Our aim over there is to understand horizontally how the rock formation changes. Hence, we resorted to profiling. Let us say we are using Venner method. We arrange the 4 electrodes like this. This is the center of the spread. We got one rho A value. Then we shifted the center point here, center point here, center point here. So, this is how we surveyed the entire profile. So, we got the data of distance versus rho A. So, this is what is profiling. Whereas, in the previous page we had seen sounding. In sounding, we arrive at a relationship between depth versus rho A. Okay. So, in sounding, so this is for profiling, I am drawing for sounding. Here is electrode spacing. Electrode spacing refers to depth. Here is rho A. So, this is the curve which we got in the vertical electrical sounding. So, this is vertical electrical sounding and this is profiling. If you combine both vertical electrical sounding and profiling, then it becomes combination of vertical electrical sounding and profiling, we are able to get the resistivity tomogram of the subsurface. Okay. How do we do this? As you see in this diagram, we conduct profiling along this line. Apart from profiling, we also conduct vertical electrical sounding at all these points. Is it clear? Does it make sense to you? That means, along a profile, we conducted profiling. That means, we had used maybe constant electrode spacing, but these electrodes were progressively moved along a straight line and we got apparent resistivity values at different distances. So, we got a relationship between distance and rho A. While doing this, we have also completed sounding at number of points. So, we got this resistivity curve also at different locations. So, both help us to understand the subsurface much more clearly, right. That means, we have completed one profile, second profile, third profile, fourth, like that. Over the surface of the earth, we have scanned the subsurface at different profiles. How do we do this? We do this in the same way as we did profiling or sounding. This is one particular sounding, which means we have just studied this particular point. Okay. In order to achieve this much more easily, at the field site, we choose, these are all our locations of electrodes, and we may make use of just a simple 4 electrode system. A simple 4 electrode system, what we do, we first keep at these 4 locations, take measurement, then at these 4 locations, by progressively moving these 4, we are completing profiling, right. Then we also do let us imagine this is the center point of the spread. We do vertical electrical sounding for this point. Similarly, vertical electrical sounding for this point, this point, this point. Okay. So, we carry out both profiling as well as sounding to understand the subsurface, right. In order to do this much more easily, right, today resistivity meters are also coming out with another tool, right. This is the resistivity meter, and the resistivity meter also has what is known as a switching device. So, what is the job of this switching device? In fact, you need not always move the 4 electrodes, but you may have 75 electrodes with you. All the 75 electrodes can be kept at the locations, and all these electrodes are also connected to a sophisticated cable, right. A cable will connect all the 75 electrodes to the resistivity meter. So, resistivity meter is connected to the 75 electrodes. I am just telling you some number, 75 electrode system. All these 75 electrodes are connected to the switching device. Switching device is connected to the resistivity meter. That means, what is the job of this device? This device automatically switches the connection of 4 electrodes to the resistivity meter. Okay. So, how does it switch the connections? It does in the combinations which you wanted, right. That means, you can set the instrument. So, I want Venner method, I want Schlumberger method, I want dipole. In all this method, I want both profiling as well as sounding. So, automatically this device, switching device, is something like a computer. It automatically switches the connections of corresponding 4 electrodes, right. Before it switches connections, it takes the measurement of apparent resistivity. So, it takes a minute to measure the apparent resistivity. After the measurement is done, the new 4 electrodes are connected, measurement is taken, then the next 4 electrodes are connected and the measurements are taken, right. So, this is how the resistivity data is obtained automatically nowadays with what is known as resistivity imaging system, right. Resistivity imaging system. What is the difference between the usual resistivity meter and imaging system? In imaging system, we have one more switching device, that is it, rest all is the same. Okay. So, the job of the switching device is to connect 4 electrodes to the resistivity meter. Though we have kept 75 electrodes at the site, at any time only 4 electrode will be connected to the resistivity meter. That job is taken care by this switching device. So, what is the advantage of this? So, we are able to get the image of the subsurface. How do we get the image of subsurface? Because this is our study area, we have kept electrodes at all these locations, right. So, when we do once profiling and sounding along this line, you have information below that particular line. What information you have? This information you have obtained during the survey. That means, we have obtained the apparent resistivity values at different locations below the surface of the earth, right. Better to look at this diagram here, right. So, what we see here is, right, when we conduct survey at the surface, we are interpreting the, we are obtaining the resistivity or apparent resistivity of all these dots, right. So, when you do vertical electrical sounding with this point at the center of the spread, we are able to determine the apparent resistivity at up to this depth, right. When you do survey from here, you are able to determine here, you are able to determine here. Okay. So, this is how all these points, at all these black dots, now we have the apparent resistivity values, right. These points can be connected. How can they be connected? All points of same apparent resistivity can be connected. That gives you the subsurface image as you see here. Subsurface resistivity image is obtained, right. How resistivity image is obtained? This is done by, this is the raw data. At all these black spots, we have the apparent resistivity data. Now, we convert the raw data to subsurface image, resistivity image. This process is known as inversion. It is something like inverse modeling we are doing. So, what is inverse modeling? These are all the points at which I have some apparent resistivity values. In order to get such a apparent resistivity distribution over this section, what is the likely subsurface formation? Is it clear? This is what is known as inversion. I have some apparent resistivity values at all these black dots. In order to measure such apparent resistivity values, what is the type of geological formations below the surface of the earth? It will assume some geological formation, it will theoretically calculate the resistivities at all these dots, and we will compare what was actually measured using the instrument at the site. If there is a good match, then the inversion is complete. If the match is poor, the model will assume a different geological configuration, arrive at numbers at all these dots, right. Then compare with the field estimated values, matching is fine, okay. If matching is not good, the iteration will be continued until we get a reasonable comparison between the model assumed or model calculated apparent resistivity value as well as field investigation which we did using the resistivity meter. Okay. So, this process is known as inversion. So, after inversion is done, we get the true resistivity cross section of the subsurface. So, this method of carrying out the survey in the field is known as 3D. First, we had seen couple of classes before, we had seen electrical profiling, vertical, electrical, sounding. Now, we are seeing tomogram or 3D. Okay. So, when we do 3D survey, we end up in getting the subsurface sections, right. Sections can be converted into true resistivity sections. How? By inversion. So, one such inversion is done here, right. So, inversion has been done and it shows the resistivity values with respect to depth. This is depth and this is distance. Whatever you see inside, they are all resistivity contours. So, in this resistivity contours, we have written, by interpreting the resistivity contour, we have written as sand and gravel. The resistivity meter do not give information about whether it is shale or clay or sand, right. We have got only the cross section as you see here in green shades, but the words inside are written by us by interpreting tentatively dark color. So, indicating the resistivity is comparatively higher for the blue color. So, when the resistivity is higher, most probably they are sand or gravel. When the resistivity is very less, light green, yellowish green color, they are all here, most probably they are of clay or silty clay type. This is how we carry on with the interpretation of the 3D resistivity tomogram. Here they try to understand the locations of higher amount of dissolved solids below the surface of the earth in the groundwater. How we are able to arrive at this? So, these are all the resistivity stations, right. The resistivity stations are indicated in black color. So, this work was done by Illinois State Geological Survey, Environmental Geology Group. They carried out a survey at a site mainly to understand about the presence of the influence of oil brines in the groundwater. So, at all these black dots, resistivity survey were carried out. That means, the black dots are center point of the electrode spread where the resistivity survey was carried out. So, we have the resistivity values of certain depth below the surface of the earth. After having completed the resistivity survey, all points of equal resistivity values were connected, right. So, we have the contours showing the equal resistivity values, which are all shown in dark lines. All these black lines, this 30 indicates 30 ohm meter contour level, contour values, right, contour lines. So, here is 30, 25, 20. At this side, the values are very less. Resistivity values are very less. When resistivity values are very less within the same site, probably indicating over there groundwater has got high salinity. So, this is how interpretation has been done by kind of resistivity tomogram or 3D. So, why do we call it as 2D or 3D? We have done resistivity sounding at number of locations along this line, along this line, along this line, as well as here. At all these sites, resistivity survey has been carried out. And what are all the broad applications of all the methods we have seen until now under electrical resistivity? Electrical resistivity methods are very widely used in groundwater exploration. We will see some case studies little later, right. And they are also used in environmental monitoring. What do we mean by environmental monitoring? Maybe how the contaminants are moving. For example, I will go back to the previous slide. So, at one point of time, these results were obtained. Suppose if you continue to investigate this site on an annual basis, what had happened to this high dissolved solids present in groundwater? Is it increasing or decreasing? That is what is known as environmental monitoring. And we can understand about the waste sites such as landfills, right, and also whether pollutants from the waste disposal sites are moving or not moving can be understood. We can try to carry out surveys for exploring ore bodies, especially metal ore bodies can be investigated using electrical resistivity methods. In engineering geological investigations, including understanding the thickness of weathered zone below the surface of the earth, can be made by electrical resistivity sounding. Subsurface imaging, we have seen some images of subsurface, right. That means, after electrical tomogram of the subsurface were identified, which is of greater importance in civil engineering, in archaeological investigations, especially when you have less resistive or highly resistive artifacts below the surface, maybe some buried sculptures made of rocks, high resistance, right, or metal artifacts, some old vessels or arms, if they are buried, they can also be easily identified using electrical resistivity survey. We can try to understand about the permafrost, right, whether it is permanently frozen groundwater will offer higher resistivity than the water in liquid form. So, often used in glaciology to understand ground stability and along the mountain slopes, right. We can carry out electrical resistivity survey to understand the thickness of weathered zone. Wherever the thickness is much higher, over there we need to give greater care to stabilize the slopes. Also used in understanding the large cavities below the surface of the earth, also to understand about the utilities present below the surface of the earth. So, in this lecture today, we had continued our interpretation of resistivity data. We have spent some time to understand the 4 classical types of resistivity curves which we are expected to get when we conduct survey by vertical electrical sounding. After that, we devoted our discussions towards 3-dimensional resistivity survey or electrical resistivity tomogram. In electrical resistivity tomogram, we conduct survey both in profiling as well as in sounding, which means we have carried out sounding at many number of locations within our study site. So, we understand the variation in resistivity in different locations vertically below the surface of the earth. Since we have done that, we are able to derive the or arrive at the vertical resistivity images. Not only along one profiles, we can conduct the survey at several profiles. So, you are able to 3-dimensionally characterize the subsurface. And in this slide, we have looked into broad applications of electrical resistivity methods. Thank you so much.